login acceptance.
Hi everyone, welcome to this session about ScalaTest and writing nicer code with ScalaTest. My name is Jacek Kunicki. I'm a software engineer at Software Mill, where we've been 100% remote from day one and where we also value full trust and transparency. If you'd like to learn more about our company, feel free to catch us at our booth down there later during the conference. So the idea for this talk first came to my mind after seeing a couple of people learning ScalaTest and seeing what code they are writing and what maybe not mistakes that they were making, but not optimal using the ScalaTest code not optimally. And this is not really about the fact that the test they have written didn't work, because they did. They were doing the job perfectly. This is rather about writing tests that give you clear error messages so that you have a lot of tests running one after another, and then you have a lot of failures and you just scroll through the failures. You are able to instantly see what has gone wrong and see error messages that are more informative than this one, for example, that false was not equal to true. So the plan for this talk is to go through a couple of techniques that you can use in ScalaTest to make the error messages nicer. We'll start with options and eithers, so with checking whether an option is defined, whether an either is defined, and what values they are holding. Then we'll look at how you can do assertions on collections, so in order to get nice error messages. We'll also talk about fixures, so verifying your asynchronous code, whether it's running correctly or not. We'll see how we can make nice assertions on exceptions and write code that looks almost like plain English. Then we'll have a look at data tables, which is about running multiple test cases or actually a single test case on a set of data. So if you are familiar with Spock, for example, in Spock, this is what the unroll annotation is doing. So you have a set of data for your test, and it runs the same test case on different sets of data. And finally, we'll have a look at a technique to apply when you want to share some setup for your test cases. So when you have a number of test cases, but there is some boilerplate setup that is repeating for every test case, and how to do it in a dry way. So that's it for the slides for now. Let's jump to the code. And as I said, we'll start with options and eithers. So here is our setup for the test. We have a single option that is not defined, so it is a none, and we have an either that is set to a left. So let's start with the options, and let's see what we can do with it. So first of all, we want to do a very basic check and see whether an option is defined or not. And one of the most simple ways that can come to your mind is just calling the isDefined method and verifying what the value of this is. So let's run this one and see what the outcome would be. So here you can see, well, the test didn't pass. That's fine, because the option was set to none and we wanted it to be defined. But the error message says that false was not equal to true, which is of course true, but maybe there is a better way to do it and to get a bit more informative error message. So in ScalaTest, we have a matter, a dedicated matter for options. And actually, instead of calling the isDefined method, we can just write that the option should be defined. So defined is a keyword that lets you do assertions on options. Now if we run it, the test is going to fail, of course. But if you look at the error message, well, it says that none was not defined. Well, you may argue that this is not much more informative than the message that false was not equal to true. But actually, if we go further into different assertions on, for example, on collections that hold options inside, then it's going to become a bit more useful. So this is about checking when an option is defined. Another thing we might want to check is whether an option contains a given value. So here, well, first, the first thing that can come to your minds is calling get, which is of course an anti-pattern, but well, you might want to do it in your test. And of course, it's going to work. But the error message that you are getting here is a no such element exception. So the test, it makes the test fail, but it doesn't really tell you what happened. So you need to guess from the types that perhaps this was about an option that didn't contain anything. So to do it in a better way, we can use a dedicated trait for options, which is called option values. And the option values trait adds a value method. So it extends the option type by adding a value method there, and lets you do the assertion this way. So that you take your option and you use the additional value method. So the value method is not originally present in the option type, but what the option values trait does is adding this value there. And here you normally use the should be. So now when we look at the error message, well, it says that it says a bit more than the no such element exception. It says that you have an option, the value was not defined, but there is actually one more very significant difference. So if we run all the tests from the option has value trait, and now here is the output of the first test case using option get. So you can just see the stack trace here. And if you compare it to the outcome of this test, you can see something that was not there previously. This is the ScalaTest failure location thing, and this is something that ScalaTest is so to say injecting into your stack trace. So it's easier for you to instantly spot where your test failed. So it actually has the line number in your test, and the ScalaTest failure location is usually at the very top of your error message. So you have a very easy way to directly navigate to your test and see what has gone wrong here. And if you just called option get, well, there is no notion of that. You need to go, here it's like the place where the error happened is visible, quite close in the stack trace, but it could also happen that it will be visible somewhere at the very bottom, so it's just easier to, and it's handy to have this ScalaTest failure location. And the ScalaTest failure location is usually introduced by if you use some dedicated matchers from ScalaTest. So there is also another way to do the same thing, so to check whether this option has a value, and this is by directly comparing to another instance of an option. So in this case, we can say that option should be sum of 1. So now this also gives us the ScalaTest failure location. So it lets you quickly find the place in the test where it has failed. And the error message is also pretty nice because it says you what the expectation, it tells you what the expectation was, it tells you what the actual result is, and that those doesn't match. And now choosing between between the option values trait and comparing to an actual option is really a matter of preference. I would say that there are neither of those has like any specific advantages over the other, but the most important thing is to have some unification of your code base. So if you decide to use a single style, just use it like through all your tests, so that when like other people are writing and reading the code, they are not wondering why here you used option values and there you just compared to options. But as you see, the messages are pretty nice in both situations, so feel free to choose any of those. We have a very similar situation with iders. So there are also 3 ways to do it. The first one is the very direct one by just calling the get method on an ider. The other ones are using the ider values traits, so this is similar to option values, or comparing directly to another instance of ider, as in line 60. Now, one thing you need to remember about here is that starting from Scala 2.13, ider is right biased. So when you get the value from an ider, so if you use for example the value method that is added by the ider values trait, you are actually talking about the right value, so the value that was on the right of an ider, because by default it refers to the right value. If you wanted to do an assertion of on the left value, so if you wanted to check for the error, then I think there is the left value method, or you need to use the left projection of the ider and call the value there. So you would do it like this. By default, when you call value, since ider is right biased, you are actually referring to the value on the right. So we can run this to see what the outputs of the test would be. And once again, the first one gives you no such element exception, and it doesn't give you the ScalaTest failure location, so this is not very useful. And the other ones behave similarly to option values, so they either tell you that the either was not right, and actually it says that it was a left, so you have some information, you have the ScalaTest failure location, and it's pretty similar when you just compare to an actual instance of an either. So we compared to the right, and it told us that, well, they don't match. So this is about options and eithers. Now let's talk about collections. So our setup for the collection is, well, a couple of collections. We have a collection called one that contains a single element. Those are all lists. We have another collection called numbers that has some 4 arbitrary elements. And we have a collection of options, which, well, its type is a list of option of int. Some of the elements are defined and some are not. And now we're going to have a look at how we can do various assertions on those. So let's start with checking for emptiness. And once again, the first idea that might come to your minds is just using the isEmpty method on a collection, because it's already there, so why not use it? And here we are getting back to the initial error message that we saw at the very beginning. Well, it says that false was not equal to true. And you probably already expect that we can do a bit more with that. And to do it nicer, to assert whether the collection is empty, we can use an empty keyword from ScalaTest. And we can say that numbers should be sorry. I'm always confusing those two. So you need to write should be as a single word and use the empty matcher here. This is one of the things that I don't like about the ScalaTest, that like at one point you write should be as 2 separate words, then you write should be with a single set of letters, and this is not really helpful. Yeah, so here you can see that actually you have a much nicer error message. It gives you the actual list so that you can see what was inside. It tells you that it was not empty, because it was not, and you have the ScalaTest failure location as well. So this is about checking for emptiness. Now, if you want to do some more detailed assertions, so check whether it contains some elements, well, you can start like that. So again, you have a built-in contains method, so why not call it and see whether it returns true or false. But you have probably already guessed what the result of those tests of this test would be. So again, false was not equal to true, which is not really helpful, although it's true. So there is another keyword in ScalaTest, another matcher to check it. And once again, you write your code so that it looks like almost like English. So now you can write that numbers should contain. And now we get to another place where the API is not unified, because previously we were not using parentheses after the matcher. Now we need to use parentheses, so actually you need to write the 3 in parentheses. And if you run it, I would argue that this error message is again much more informative, because first of all it gives you the entire list, then it gives you the element that you were looking for. So once again, the test would work no matter how you write it. But if you imagine having a lot of test output and then just scrolling through it, it would be probably much quicker to see why it's failing if you encounter such error message than if your message only says that false was not equal to true. Now let's look at a specific use case where you have a collection that you expect to contain only one element, and because there is a specific a special matcher for this case. So again, the most intuitive way would be to check the size of the collection and then check the first element, so the head. Here you can see that actually, if you wanted to check for the size of a collection, you are not going to call size and compare it to a number, but there is a dedicated matcher for that. So you can just write that 1 should have size 1, and then the head should be 1. And this works, of course, because why wouldn't it? But there is a nicer way to do it with only a single line. And this is done using the lone element method, which is added by the lone element trait here. So this makes 2 assertions at one time. It checks both for the size, and for the actual element. So you can say that one lone element should be 1. And well, it passes because the element is 1. Now let's experiment and then see what happens if the test fails. So if we change the element to the expected element to 2, it's going to fail, well, because 1 was not equal to 2. And for example, if we substitute the collection here from the one that we know that contains a single element, but we can put numbers here, and numbers has more elements because this is a 4-element list. And now we can see that it actually also checked for the size, because we were expecting a collection that has only a single element, but it contained more. So this is like a proof that it actually not only checks for the element, but it looks at the size of the collection as well. So now let's say that we want to compare two collections between each other to see whether they contain the same elements. So first we start with a very simple case and just like write it in a, say, normal way. So we take our numbers and we can say that numbers should be, and it's a list, and we have 2, 4, 5, and 6. 2, 4, 5, and 6. So this is going to pass as expected. But what happens if for example, this wasn't a list, but if it was a set? So we actually maybe we don't really care about the type of the collection, but we want to look at only at the elements to see if the elements are the same. And using this approach, this is going to fail because, well, the types don't match. So the elements inside are the same, but a set is not the same as a list. So this doesn't work. But actually, there is a dedicated matter for that, so for checking whether, like for disregarding the type of the collection. So if you only want to check whether the collections contain the same elements, no matter what the type of the collection is, you can write something like numbers should, and now there is contain, and the matter is called the same elements as, and we can take the set from here. So now you see that we are actually comparing a set to a list. They both contain the same elements, but the type of the collection is different. But the test still passes, which is nice. This, however, doesn't care about the order of the elements. So no matter what the order of the elements was, actually this is a set, so it doesn't have any order by definition, and still the test passes. Sometimes, apart from checking whether the collections contain the same elements, you also want to check for the order, so whether the order is preserved as well. So now we can use another matter, which is called, which is similar. So it's numbers should contain, and now this is the same elements in order as. And let's start with, let's take a list here, so we actually have some order. And now run it. So this passes because the collections contain the same elements, the order is preserved. But if we reverse the list, for example, now you can see that it doesn't pass because we broke the order. So the order is not as the original. And we can double check that the previous matter actually doesn't care about the order. So if we use list reverse here, the test still passes. So two different test cases, and depending on what is your expectation. So whether you only care about only the same elements being present in both collections, or if you care also about the order, based on that you can choose one of those. So one more thing about checking and making assertions on the elements of the collection is whether you want to check something. You want to check a predicate, whether it applies to some of the elements in the collection, whether be it like all the elements, some of the elements. So let's say that, for example, we want to check whether the value of each element of our collection of options, so of this one, whether it's 1. So we have the option value straight already, so this tells us that we'll be using the value method added to an option. And the most intuitive way to do it would be to take the options collections and then run for each. And then for every option, we call the value method and make an assertion that the value should be 1. Of course, this test fails because in our collection, some of the options were not defined. Those that were defined, not all of them contain the value of 1. But here the error message is pretty mysterious, although we use the option value method, because, well, it tells us that one of the options was not defined. But we are working on a collection, so probably we would like to know which element made the test fail and to have any more details about what has gone wrong inside. So, of course, there are dedicated methods for that. And there is an object called inspectors that gives you, for example, a for all method. That you run on, sorry, it's not numbers, it's options actually. And then you just make the assertion in a very similar way as here. So there is this second set of arguments where you put the assertion. And now the test failed again. But you can see that the error message contains much more details. So it tells you that which element in the collection caused the problem. It gives you the entire collection, so you can verify that it's actually true what the error message is saying. But what you can notice here is a fail fast behavior. So there is more than one element in the options collection that doesn't match the value should be 1 predicate. Because actually only the first one is the one that matches, the none doesn't match, the sum of 3 also doesn't match. But if you look at the error message here, you can see that it detected the first element, the none, that doesn't match, and it stopped. It may happen that you actually want ScalaTest to go through the entire collection and verify all the elements, and this is possible using another helper method from the inspectors, which is called for every. And now again, you pass the collections, you pass the collection, you pass the assertion, and notice what the error message here would be. So here it also failed, but it went through the entire collection, and it gives you error messages for all the elements that didn't match the predicate. So depending on your use case, one of those might be more useful than the other. And now a word of explanation why use the inspectors trait here, the inspectors object, and not use the why not import it? And this is because the for all method is also present in some other traits in ScalaTest. We'll be looking at this a bit later. So just for clarity and for giving for showing your intention and what you actually want to do, it's just safer to use the inspectors object directly and call the for all method from the inspectors. Because if you only imported this trait, it would be fine. But if you also somewhere in the same test case, if you imported some other traits that also define the for all method, then you can get confused, and those for all methods serve completely different purposes, and it would just be confusing. So to be on the safe side, just use the inspectors and prefix the for all, for every, and the other calls. And looking at the inspectors, you can see that there are actually much more different assertions. So you have, for example, for at least, for at most, for between. So this lets you do some very precise assertions on the collections, depending on what you want to check actually. So it's nice to familiarize yourselves with what the inspector trait offers. So that's it for the collections. And now let's look at some async code. So the code that we'll be testing is a future that does some very basic thing. It just sleeps for 1 second. So we are simulating some slower behavior here, and it gives you a value of 1. And since futures in Scala are eager, which means when you call the future apply method, and we are doing that here, the future is immediately executed. You need to provide some form of thread pool for the future to be executed on, and that's why we are explicitly providing the global execution context here. Of course, depending on your use cases, it's not always reasonable to use the global execution context, but this is out of the scope of this talk, and we are only using it for demo purposes. Okay, so the initial idea when we want to verify what happens with a future is using the await object, which is this is a Scala built-in, and it gives you 2 methods actually. So you can either await for a result. So this is useful when you're interested in the value that the future is returning. Or you can use the await ready, and this means that you are disregarding the value of that the future holds, but you're only interested in the completeness. So we're using await result here, and then doing a normal assertion on the result. And we are waiting indefinitely, which is not always safe, because theoretically you should always have some limited timeout, because if you wait indefinitely, it might mean that your code is not working correctly, actually. But with this indefinite timeout, we can see that the test is passing. So now let's see how we can do an assertion using some nice stuff from ScalaTest. And this is done using the Scala futures trait. I'm always confusing it with option values and either values, because for the Scala futures trait it also adds a method to the future. The method is called future value. And like if you're using option values or either values, I would expect this to be named future values, but it's not named. It's named Scala futures, not future values. So be aware of that. Nevertheless, when you take your future and you have this Scala futures trait mix in, you get the future value here. And now this already gives you the integer. So this is a future of int, but the future value method gives you the int. So it does the blocking wait for the future. It gets the value, and then you can do a normal assertion on that. But we can see that the test is failing. So the question is why. So if we look at the error message, you can see that it waited 150 milliseconds. And our future is sleeping for a second. So, well, now it's not a surprise anymore that this has failed. So here you notice that when using await, we needed to provide the timeout explicitly. And here in using the future value, we are not providing anything. So, well, of course, it has some timeout. It has the notion of waiting for a limited time. But this is passed as an implicit parameter. So if you look at the implicit parameters of future value, you can see a patience config parameter, which is using some default patience config. And if we dive deeper into the source code of ScalaTest, you can see that this is actually 150 milliseconds. So this is where it comes from. So that's why this failed. The nice thing about using the patience config as an implicit parameter here, and implicits, you can think of implicits as a way to provide context to your code, some kind of context. So here, if you want to override the default patience config, it's enough to define an implicit patience config with a different value somewhere in your scope. And actually, there is a trait that is built in ScalaTest in order to wait a bit longer, because the default patience config is 150 milliseconds. And for test cases where you don't do any I/O, don't do any long-running computations, this is usually enough. But if you are doing, for example, some integration tests, for which probably 150 milliseconds is not that much, you can use the integration patience trait, which, as the name suggests, was created with integration tests in mind that need to wait a bit longer. So this actually overrides the default patience config that was in the 150 milliseconds, and you can see that the test passes now. And we can see that in the integration patience, this is actually 15 seconds, so it's much longer. If in your use case this is too long, you can of course create your own implicit value of type patience config and put anything between those 150 milliseconds and the 15 seconds there. So this was one way of looking at futures using the future values trait, but there is also another approach that you may find useful. And this is this is done using the async flat spec. So far the base trait that we were using, I'm extending the base spec everywhere, and the base spec extends any flat spec. So this is the default one that we are using everywhere. But here you can see that instead of any flat spec, I'm extending async flat spec. And the difference between async flat spec and normal flat spec is that in the async variant, you don't return an assertion, which is what you normally do when extending any flat spec, but you return a future of an assertion, and ScalaTest is actually taking care of evaluating this future and checking and verifying the assertion. So then we would take our future. Sorry, the future is defined somewhere above, so we'll just create a new one, a future of 1, and then we need to return a future of an assertion. So we want to convert our future of int to a future of an assertion. So you're using map for that, and the assertion that we want to return is that the value that we have here should be 1. And here in the map, we are operating on the int, so we don't use the future value anymore. We just like our predicate is on an int. And it passes as expected. So now we have an example that looks pretty similar, although the difference is that we are not using map, but calling future value on that. We have a different future, but we also have a different expectation. And now if we run it, this fails. And it says that it like waited 150 milliseconds and it didn't get the expected result. Well, this is an instant computation, so for sure 150 milliseconds is enough. So the question is, what happened here? Well, if we look at the code here, we remember that the future apply method, it needs an implicit execution context, because this is a thread pool that you are providing for the future to be executed, because this starts the computation immediately. So, and you can also notice that we didn't provide anything here. When creating the previous future here, we provided the global execution context as the thread pool. And here we didn't give it anything, but of course it must have come from somewhere. And it turns out that it has come from the async test suite, which is the base test case or the base class of the async specs. And now if we dig deeper, you can see that this is something called serial execution context. And then if you dived even deeper and looked what the implementation is, it turns out that this is something very specific, because the serial execution context, so the one that is brought in the implicit scope by the async flat spec, this isn't actually a thread pool, but it's a queue. And whenever you try to run something on this execution context, the task is put into a queue, but it's not executed. And the point when it is executed is only when the entire test code completes. So actually when we try to run this feature here, it's not actually run. It's put on the queue of this serial execution context, and then it would be evaluated only when the body of the test completes. And the value of the body of the test would complete when the future value method completes. So we have a deadlock situation here, because we have one future waiting in the queue to be executed, but it would only be executed when this future completes. But this future won't complete until the previous one put on the queue executed. So you need to be aware of that. This actually hit me when I was first using async flat spec. So the message from here is that when you are using async flat spec, you either should not be blocking in your test code, which is what we did with the future value method here, or you can use another execution context. So if we explicitly said that we want to run this future of 2 on a specific execution context, like the global one, then it's going to work. Because this no more uses the serial execution context that came from the async flat spec, but it uses the global one, so it's a normal thread pool. The future was created, it was run, and then the future value method was evaluated. So be aware of that, and if you choose the async flat spec style, be careful not to put any blocking code there, or use proper execution context. That's it for the futures. Let's now talk about exceptions. So how to verify if your code did something wrong, actually. So the first example, okay, to start with, we have our custom SumException class. We have a misbehave method that is throwing this exception, and we will be using this misbehave method in our test code. And now this is actually a counter example. This is something that you should not be doing, because this is very imperative code that, well, it checks for the exception, but you can do much better. So what this code here does is creating a Boolean flag, a mutable one, then calling the code using try catch, and then in the catch it actually sets the flag to true and verifies whether it was set to true. Of course, this would do the job, but you can do it much nicer and in a much more declarative way using some other matches from ScalaTest. So I'm going to fold this so you don't look at it for too long. So there is a couple of ways to make the assertions on exceptions. The first one is called assert throws, and you give it the type of the exception that you are expecting, and you call the method. And this works as expected. Well, the test has passed. There are a couple of other ways to approach this. So one of them, we are going towards a direction when you write more English than Scala. So here we can say that using the thrown by, that a some exception should be. Now we are using the thrown by matter, and okay, this time I think it should be, yeah. So it's confusing, as you can see. So this reads like a sentence in English almost, and also does the job because the test passes. If, on the other hand, you want to verify whether an exception wasn't thrown, there is a no exception matter, and then you also use the thrown by. This is going to fail, of course, because our misbehave methods is throwing an exception, but still it reads nicely. And actually, if you want to be grammarly correct, you even have the N variant for that. Of course, the compiler won't check the grammar for you, but you can make your code even more beautiful. So this is still going to pass, although the some exception starts with S. Now let's say that we don't only want to verify whether an exception was thrown, but we want to make some specific assertions. For example, check what the message was. So there are also a couple of ways to do it. The first one is calling the intercept method, and actually, yeah, you put the exception class here, the one that you're expecting. You put the method here, then you can assign it to a value, and you can do a normal assertion on the message. So normal means using should be, I don't know, anything. So now when you run it, it fails because the message didn't match. But going towards more plain English, we can use the keyword. And this is, well, it might look similar to the A or N that we were using previously, but A or N don't give you the instance of the exception. But the gives you an instance of the exception. So if you say the some exception thrown by misbehave, this actually gives you the instance, and you can do the assertion on this. And it reads nicely. And of course the test is going to fail, but this was expected. And now the most beautiful way to do it, if you only want to check the message, because those examples gave you access to the full instance of the exception, so you could check the message, you could check anything else as well. But if you only want to check the message, you can actually write something like this: the some exception thrown by misbehave should have message, and that message is the matter for specifically for the exception message. So you can write something like that. It reads almost like English, apart for the braces, and it also fails. So depending on whether you want to verify the entire exception, so if you want to check something else than the message, then you use either intercept or the. And for the full instance, if you want to check specifically for the message, then you can use this approach with the have keyword and the message matter. Next thing I want to talk about is data tables, and this is for. Well, I want to collapse everything for now. This is for doing assertions on a couple of test cases. So we want to write a single test case, but then we have a couple data sets for this single test. So here we'll be working with a list that contains 3 tuples, and our test would verify whether the third value in the tuple is the sum of the 2 previous ones. So of course you can see that this test case should be failing, the other ones are valid. So let's see how we can approach that. Well, the first thing we could try is just taking the values and running the for each method. And it gives you the A, B, and C. And then you do the assertion normally. So you say that A plus B should be C. This fails. It tells you that 2 was not equal to 3, which is of course true, but it doesn't tell you which of the test cases actually caused the test to fail. And in such scenarios, we would like to know that, especially if the test set is bigger and you don't want to manually go over all the cases to check which one was the failing one actually. So there are 2 approaches to do it in a nicer way. One is about generating a separate test case for each of the values from our test data. And this is done in a similar way like we did here. But we are starting with the loop and only creating the test method inside. So what we will do is write the test here. And we can say that it should, for example, compute, and this is a string actually, that we want to put our values inside, and we want to compute that A plus B equals C. Now this is important. It's important that we are putting the values that change with the test data here, because ScalaTest expects that the names of the test would be unique. So if we didn't do it, if we only put like it should compute sum here, it would fail because we would get an exception from ScalaTest saying that the test names are not unique. So this is important that we do something like this here. And we use the same code for the assertion here. So it looks like that. Oh, and we're missing an in. Yeah. So now you can see that after we run it, there are actually 3 separate test cases. So this might be useful because the name of the test case tells you what the expectation was, and here it says that 2 was not equal to 3 again, but you know precisely from where it came. Another way to do it using some built-in from ScalaTest is using the table-driven property checks trait, which is a bit similar to Spock's unroll. The syntax for that is not as nice as in Spock, but it does the job. So you do it using a table class. And the table has a specific structure, so it contains the first element of the table is the names of the rows in that table. So in our case, they are called A, B, and C. So this is a tuple, and the rest you can see. Looking at the asterisk here, that this is a varargs argument where you put all the actual test cases. So we are taking test data values, and we tell the compiler that it needs to treat it as a varargs argument, because we don't want to put a single element which is a collection here. We want to take the collection and explode it to a varargs argument. That's why we are using the syntax here. And now, this is the case where we have another for all method, so like the one that we used to make assertions on collection elements. This is the for all method also exists in the table-driven property checks, and this is the place where it can get confusing. Now we can just take the assertion from here. Yeah, something like that. And now when we run this, well, this is now a single test case, so it didn't explode into a number of test cases. But when you look on the error message, you can see that this is very detailed, because it tells you that, well, the actual error message, that 2 was not equal to 3, but it also tells you where it was located in your table. It tells you what the values were, and it tells you what the name of the parameters are. This is why you provide the first row in this data table to provide the labels for the numbers or for the values that would be used here later. So thanks to that, you are getting a very nice and informative error message. All right, so far we've talked about using different specific matchers for different assertions. And now for the last part of this talk, I would like to tell a bit about avoiding boilerplates. So about a case where you share some test cases, or actually you don't share the test cases, but you have test cases that share some boilerplate code. So, for example, in every test case, you want to do some setup, provide some initial values. You want to do some so-called tear down logic. For example, you want to close a resource or anything like that. So let's say that we are testing some notification service. We start with some given block. We construct the notification service, and it has some values. It has a prefix for the notifications that it's sending, and it has 2 more dependencies. It depends on the user service and on the notification repository. So we'll need some user service and some notification repository here. For now, we don't have the values, so of course we need to provide them, and this is the setup that we are doing. So we create our new user service, assign it to a value. We create the notification repository and assign it to a value. So this is now good. We'll also need the notification service, so we're assigning it to a value. And now we are doing our actual test logic. So now we are calling notification service notify. It takes some user ID, and it takes some message for the notification. So it would be hello Devoxx. And now we do the actual assertions. So now we say that notification service, and we have a method to find the notification by a user ID. If you look at the type, it returns of a future, of an option, of a notification, and we want to assert the message actually. So let's take the message from here. We are using both the future values and the option values traits here. So first we take the value from the future, then we take the value from an option, then we take the message, and then we say that it should be, and this is our expectation, and also it also takes the test prefix here. And there is one more thing we need to do, because let's say that we need to close the notification repository somehow. So what we're doing here is wrapping this into a try and finally, and we say that notification repository shut down here. So let's now run it, and we can see that it fails actually. And the reason it fails is that the future that we are evaluating here is not completed by the time we evaluate it. So we would like to use another technique here to say that we want to wait until the future is evaluated to a specific value. And for that, we can use the eventually block from ScalaTest. So we can say something like that. And this tells ScalaTest to wait, like it's an active loop, and it just checks the future periodically until this checks the assertion periodically until it's true. Of course, there is some timeout, but we are using the default one here. And now the test passed. You can see that the shutdown logic was executed, so this is all good. And this is perfectly fine. Like there is nothing wrong with this approach until you want to write a similar test again, which does something very, very similar, but for example tests a different method. So let's say that we are doing something like this, and here we are not calling notify, but we are calling a do something else method. It only has the user ID. It doesn't really matter what it does inside. And we do some assertion. Let's just say that the test is going to succeed here. And now if you look at those two test cases, you can see that the only places where they actually differ is here, when where you call another method from the service, and here when you call the assertion. But all the other stuff is very similar. So there are a couple ways to solve it. I'm running out of time, so I will stop live coding now and just show you how you can do it. So there are two approaches to that. One is using something called fixture spec. And what you do here is you provide a class that has this required setup. So here this is the user ID and the notification service. And then you override with fixture method that is responsible for providing all the boilerplate code. So you can see that here we are actually doing the initialization of the notification service. Here we are doing the cleanup logic, the shutdown. And here in a kind of specific way, we are calling the test method, passing the fixture there. So this is how you can do it. And then if you create a test with that, you can see that since we are using the fixture spec, we are getting an additional parameter here, and this is the instance of our fixture. So this is the entire boilerplate. And if you write more test cases, you would have access to this fixture there, and you will be able to use it. And now using this trick with importing things from a concrete instance of this fixture, you don't need to prefix all the calls here with the F. But instead, you are just working with the notification service, but you don't need to repeat the setup everywhere. So this is a way to solve it, and it's really useful when you want to stay dry and to avoid the boilerplate. So that's it. That's all I had for today. We went through options, iders, collections, futures, exceptions, having a number of test data for a single test case. And we also saw how you can stay more dry, looking at using the fixtures in order not to repeat your test code. If you're using Scala and you haven't yet subscribed to Scala Times, our Scala newsletter, I encourage you to do so. There is a lot of great content here, so feel free. And that's it. The entire repository is available on GitHub, so if you want to look at it later, feel free to go there, and this should just work when you download and run the code. Thanks a lot. If you have any questions, I'm here or I'm there later during the conference.